Good morning, everybody. Welcome to this IEC 61511 Proof Test Design and Planning webinar, one of Exodus free webinars. As you may know by now, the audio will come over your PC speakers. We have disabled your audio, so any questions, concerns, etc., feel free to ask those through the Q&A menu that is on the top of your Windows Live Meeting dialog box. This webinar today is as of course the title says, we'll talk about proof test design and planning, and there are some various schools of thought on these. I'll try to talk about what the standards require. I'll also try to talk about what some people like to see in the industry. As I start, let me introduce myself. My name is Iwan van Buren. I am a certified functional safety expert. I'm the Director of Engineering at Exeda, where I support end users in compliance when they want to achieve compliance to IEC 61511 or the NCISA 84.00.01:2004 IEC 61511 modified standard. I help manufacturers in achieving compliance to IEC 61508, and I also perform functional safety audits and certifications on both end user and manufacturer projects. And of course, projects that we're consulting on, someone else will do certification, and if I do certification on a project, I will not do any consulting on that. But that's just a separation between consulting and certification that we maintain. I'm responsible for the development, maintenance, and certification of the Excellencia Integrated Safety Lifecycle tool. Some of you may be familiar with that as well, and there are some features in Excellencia that we're making available to people to assist in creating proof test procedures. As I mentioned, perform 61508 development support, functional safety assessments, audits, variety of reliability analyses, SIL selection, SIL verification. I'm an Exeda and an ISA instructor for our functional safety classes. For those of you who are not that familiar with Exeda, Exeda is a knowledge company, consulting company with a variety of offices around the world. We have two official headquarters. One is in North America, in Sellersville, that's in Pennsylvania, in the Philadelphia area. And one is in Munich, in Germany. It's our European headquarters, and those are our two founding fathers, so to say. One is Bill Goebel, the other is Rainer Faller. In addition to that, we have a variety of offices around the world, offices in the UK and Canada. We have a legal entity in South Africa and Mexico. We have someone in Brazil as well, in New Zealand. So we're spread out around the world with consultants that either do development support, IEC 61508 type of work, or IEC 61511 type of work, end user support. Variety of industries as well, primarily the process industry. We do have some industries like the machinery industry, the automotive industry, the nuclear industry, where we do some work as well. With regard to our Excellencia engineering tool, we have a product that will assist in alarm management rationalization. We have a process hazard analysis import utility that will basically extract, depending on how you've implemented your PHA, that will extract safety and semantic functions or potential safety and semantic functions out of your HAZOPs and import them into the Excellencia software, which has a SIL selection tool using hazard matrix, risk graph, layer protection analysis,
it has a safety requirement specification tool, a SIL verification tool. Some of you may already be familiar with the Silver tool. We have an extensive failure rate database, equipment item failure rate database included in the tool. A variety of parameters, and arguably I'm a little bit biased, but a lot of detail that can be put in the tool for relatively accurate SIL verification analyses. We have a proof test generator, and obviously, given that this is the proof test design and planning webinar, I'll talk about that a little bit more. And of course, the objective of these engineering tools is to end up with a cost-effective implementation of the functional safety lifecycle standards. We also have published several reference books, and actually not all are listed on this slide, but up to now, all ISA books that have been published by ISA on the topic of safety and reliability have been authored or co-authored by Exeter partners, employees, etc. Some may have left Exeter since, but the original authoring was all done by Exeter. We've published some of our own books. For example, we've published an electrical and mechanical component reliability handbook. We have the safety equipment reliability handbook, which is the basically paper format of the equipment database that is part of the Excellencia software. We also published a final element in IEC 61511 applications book that talks about several aspects that one should consider when implementing safety and cemented functions, specifically then with regard to final elements. We have, as I mentioned, several offices around the world. We're a consulting company, but we also have a certification division. And the headquarters of the functional safety division is in Geneva in Switzerland, which is the home of the International Electrotechnical Committee. And as I mentioned before, there are a variety of our consultants that will perform assessments, certification assessments, but these are always independent of the actual consulting services that have been performed. And up to this point, we've done more process industry product certifications than any other company in the world. So it's definitely a very it's a very good match to our consulting services. So when we talk about the IEC 61511 standard, and that's going to be our focus today, there are two fundamental concepts. One is a safety life cycle that basically prescribes a detailed engineering process, and we have a probabilistic performance-based system design. The life cycle approach makes sure that you go through a very rigorous process, that you cross your T's, dot your I's, and sometimes people tend to focus on that aspect with regard to the software reliability, application software, that is then, and the objective is to avoid systematic faults, avoid design mistakes by having a rigorous development process that you would go through. The probabilistic performance-based design is typically focusing more on hardware reliability, probability of failure, or random failures. The beauty of this is that the beauty of the concept of the performance-based design is that you can implement whatever you want for your safety and cemented system, as long as you can demonstrate by means of probabilistic calculations that your solutions are safe enough. The disadvantage with that is that the standards don't tell you what to do. You have to come up with your own solution. So with any advantage, there are obviously disadvantages, but as long as you can demonstrate that your solution is safe, you can implement that. So if you want to use wireless technology in safety and cemented system, no problem, as long as you can demonstrate that it is safe enough. And typically that will mean if you lose communications that you go to a safe state.
The random failure protection or hardware reliability probabilistic approach is basically expressed in a couple of different methods, but one of the requirements is that your specific safety instrument or function meets a certain maximum probability of failure requirement for a given SIL level. So if we talk about the average probability of failure in a month, which is the metric that is applicable for low demand mode applications, we can see that a SIL 1 safety integrity level requirement means that my average probability of failure in the month needs to be less than 10 to the minus 1 or less than 0.1. If I want to claim SIL 2 safety instrumental function, my average probability of failure in the month needs to be less than 10 to the minus 2 or less than 0.01. SIL 3 less than 0.001, SIL 4 less than 0.0001. So these are order of magnitudes levels that represent the amount of risk reduction a safety instrumental function provides. So low demand applications are typical process industry application. There are also some applications that are quantified as high or continuous demand mode, and for that particular situation, the average probability of failure in the month no longer applies. We need to look at what is called the probability of failure per hour. Given that it's a probability per hour, it's not really a probability, it's a rate, but it's basically the equivalent dangerous undetected failure rate of your safety instrumental function. Also for SIL levels, and you will see here that SIL 1 you need to be less than 10 to the minus 5, SIL 2 less than 10 to the minus 6, and so on. Compare the two tables. You will see that there are roughly 4 order of magnitudes difference between the SIL levels in the P of the average table versus the SIL level in the P of H table. The 4 orders of magnitude correspond to the approximately 10,000 hours in a year, 8,760. So you see what the relation is between those two tables. What's the difference between low demand and high demand or continuous demand? Basically, as long as you can claim that you have at least one proof test interval or one proof test executed during a demand interval, that will be considered a low demand. And the rule of thumb there is that the proof test the demand interval needs to be at least 2 times larger than the proof test interval. So if you have the 2x difference between a proof test interval and demand interval, then you typically are in a low demand application. If that's not the case, if your demand interval is not 2 times greater than your proof test interval, you're either high demand or continuous demand. And the distinction between high demand and continuous demand is made in the speed at which demands occur. And basically, if the demands occur that rapidly that you are not able to basically respond to detected failures, so basically you're not able to do anything when a failure is detected in your safety instrument function, then that will be classified as a continuous demand. If you are able to react when there is a detected failure, then that will be considered a high demand. So there's typically a 10x difference between the worst case diagnostic time interval and the demand interval would be the difference between high and continuous. And of course, you need to look at speed of response of operators as well. As a quick example, if you look at an operator in a automobile manufacturing plant who is pushing sheets of metal in a big press, that safety instrument function basically needs to work continuous. Even if it detects a failure, then arguably the operator that pushes a sheet of metal in the press every minute or so doesn't have time to react on any detected failure. High demand example could be that you have a proof test once a year and your demand interval is one per year. So you don't have the 2x difference, therefore you cannot claim that there's always at least one proof test in the demand interval, and concept of average probability of failure demand does not apply anymore, and we would talk about a high demand mode application. So when it comes to the probabilistic performance-based system design, there are a total of 3 requirements that a safety instrument function must meet or the conceptual design of that function must meet in order to meet a specific safety integrity level. First of all, the individual components or equipment items need to have a certain SIL capability or systematic capability, which basically means that the products are either IEC 61508 certified, or the end user has sufficient documentation to prove that there is adequate proven in use experience with these components, that therefore there is no systematic problems in the product. So that's number one. Number two, that the individual subsystems of a safety and cement function must meet the architectural constraint requirements, and there are some requirements in IEC 61508 that talk about different types of components, type A and type B, and safe failure fractions, and then based on the SIL level that you want to achieve, you will need to have a minimum hardware fault tolerance, a minimum level of redundancy. Now, that's what is called the architectural constraint. IEC 61511 is a little bit different in that for field equipment, it doesn't talk about safe failure fractions, it doesn't talk about type A, type B equipment, it simply talks about minimum levels of redundancy. For SIL 1, no redundancy, SIL 2, 1 level of redundancy, SIL 3, 3 levels of redundancy, which is basically a 1 out of 3 voting. So that's the second requirement that your performance-based systems need to meet. And then the third requirement is that the average probability of failure on demand, or if we talk about a high demand application or continuous application, the probability of failure per hour must be in the range of the given SIL level for the entire safety and semantic function. And that's basically what we saw on the previous slide. As I mentioned before, in the process industry, the majority of our applications are low demand. Every now and then I come across a high demand application just because the proof test has basically been extended so far that we cannot take credit for the proof test from a probability of failure perspective. But the majority is low demand applications, and that's what we will be focusing on the rest of this webinar. And the question that is basically put on the slide here is, how does the proof test improve my average probability of failure on demand? The reason that we're calculating an average probability of failure on demand as a measure for a low demand application is because we are going to take credit for proof testing that we perform, and that's where we're going now. On this slide, what you see is basically a way to account for proof test coverage. Now, keep in mind, this is a simplified equation for a 1 out of 1 architecture. It's very simple, but it will help to bring the concept across. A P of the average is basically the sum of a portion of the safety and cemented, a portion of the safety and cemented function that will be accounting for dangers and detected failures that will be detected during proof test, and a portion of that safety and cemented function where the dangers and detected failures will not be detected during the proof test. So what we see here is the proof test coverage multiplied with the dangers undetected failure rate times test interval divided by 2. That's the portion that will be detected. And then we have the second term, that is 1 minus the proof test coverage multiplied with the dangers undetected multiplied with the lifetime or operational lifetime of the plant divided by 2. So in the extreme, if we say that my proof test coverage is 100%, then my average probability of failure on demand formula will simplify to dangers undetected failure rate times the test interval divided by 2. The second portion of the equation will basically drop to 0. And the other extreme, if we assume that nothing is detected during the proof test, in that case, my average probability of failure on demand is basically the dangers undetected failure rate times the lifetime divided by 2. So if you consider that your test interval may be 1 year and your lifetime may be in the order of 10 years, you can see that going from one extreme to the other, we will have an order of magnitude difference in the average probability of failure on demand that is calculated, and therefore we have a SIL level difference in the result. So the proof test coverage is a parameter that can have a significant impact on your average probability of failure amount that is calculated if the proof testing that you perform are not adequate enough. So okay, so let's look at what the objective is of proof testing. You can look at the IEC 61511 standard or the S84 standard, and you will see that there are a couple of definitions in there, and there is one clause in the standard that will say the objective of the proof test is to detect as many dangerous undetected failures as possible, and a little bit further on there's actually a statement that will talk about undetected failures in general, so it doesn't make a distinction between dangerous and safe failures. So from a average probability of failure on demand perspective, from a functional safety standard perspective, the objective of the proof test is to detect dangerous undetected failures. If you have a perfect proof test, your proof test coverage will be 100%. If you have arguably your worst case scenario, you will not detect anything. Your proof test coverage is 0%. So just as an indication as to what is the effect of this proof test coverage on my calculated probability of failure on demand. Just as an illustration here, I didn't calculate the average probability of failure on demand. I just calculate the probability of failure on demand as a function of time, and you will see the three scenarios that I chose. 100% proof test coverage is the blue line. It basically goes up to a certain level, then drops back all the way to 0, and repeats itself from there on. We have proof test coverage of 0%, that's the top red line, which basically goes, well, starts out the same as the 100% coverage, but obviously when you perform the test, you will not detect anything, so PFD will simply continue to increase as a function of time. And then we selected 85%, which again initially shows the same thing, but then what you can see here is that when you perform a proof test, that PFD will not go all the way back to 0. It will continue to increase slowly, so that basically accounts for that portion of the failures that are not detected during the proof test. That is the increasing line that you see, and then the sawtooth behavior is basically the portion of the failures that is detected as a function of the proof test. So you basically have a combination of the top and the bottom line, and that's what proof test coverage does as a function of to PFD average, to probability failure on demand as a function of time. So, if we look at a conventional proof test approach, then one could argue or look at a statement: the purpose of the proof test is to verify that the safety instrument function works properly. It is assumed that if it works properly, it has not failed. That is the conventional proof test approach, and you could look at a specific transmitter proof test procedure where we would block the valve from closing, move the input signal above a trip point, verify that the valve attempted to close, move input signal back to normal below the trip point, and remove the valve block. Okay, what we've done now is we've demonstrated that my safety function works. Can we assume 100% proof test coverage, 100% diagnostic coverage here? Well, the purpose of the proof test is to detect any failures not detected by automatic online diagnostic, dangerous failures, diagnostic failures, and parametric failures. The objective is not to verify that my safety and semantic function work. The objective is to detect any failures that are undetected by the automatic diagnostics. So this is maybe a little bit of an extreme approach. And obviously, when you are performing a proof test, it would be nice to demonstrate that your function is able to do what it's supposed to do. But from a probability of failure perspective, safety integrity perspective, the objective of the proof test is to detect any failures that are not detected by automatic diagnostics. So, given that objective, and this is not something that Exeter came up with, this is what is written in the standard, what we need to do when it comes to a proof test, we need to design a proof test procedure that is able to detect those failures that are undetected by automatic diagnostics. And if we are able to focus our proof testing on the detection of those failures, then arguably we can come up with easier to perform procedures that cost less, arguably more likely to be executed. But in order to do that, we need to know what the actual instrument failures are that we need to look for. What are the failures that we haven't detected during normal operation? So how do I get a list of dangerous undetected failures for the instruments I use? There could be a variety of instruments that you're using, and there's a certain amount that will be undetected by any automated diagnostics, and how do I know what those failures are? One of those techniques that one can use is a failure mode effective diagnostic analysis, where based on individual component failure rates and failure modes distribution, a overall product failure rate is determined and product failure modes. So by looking at the individual components of, for example, a transmitter, look at the failure mode distributions of that transmitter, you will be able to determine what the output effect is on the overall transmitter level. The FMEDA is an analysis technique that will identify all dangerous undetected failures in a product. The technique uses a database of component failure rates and failure modes. The result is a failure rate for each failure mode of the product, including dangerous undetected failures. So if we look at a transmitter, what type of failure modes do we have? Well, we have failure modes that are classified as dangerous. For example, my output is frozen. That is dangerous. And since it's in the normal operating range between 4 and 20 milliamps, then arguably this is not something that I will not be able to detect by a PLC that is connected to it. So arguably there is a dangerous undetected failure. I can have a failure that will cause the output to go over range, saturate high. I have a failure that could cause output to go under range, saturate low. And those are either safe or dangerous, detected or undetected, and it all depends on the ability of the PLC to detect overrange, underrange, and the actions that the PLC takes as a result of that. Other failure modes, output cannot get to 100%, output cannot get to 0%. Arguably those are dangerous. You don't have full control over your active scale. Internal automatic diagnostic circuit failure may not necessarily be an immediate dangerous or safe failure. It could be an annunciation failure. That's what the letter A stands for. And depending on if there is a temperature compensation circuit, if that fails, depending on the type of failure, that could be arguably anything. So that is something that we only know. That we only know when we look into detail on a specific component. I have a question here. Must we make a leak test of a block valve? Is it possible to do this inline? I will address that question in just a bit. So I just wanted to let you know I did see that question. I will address that in just a bit. So this is an example of transmitter failure modes. We can also talk about actuator failure modes. If there's severe leak, loss of air pressure, assuming this is a spring return, then arguably there is not enough pressure to withstand the spring force. Therefore, you will go to whatever the non-energized state is. Assuming we're doing de-energized to trip, you will go to a safe state. If there's a clogged air inlet or trapped air or something is jammed or damaged, etc., those could be dangerous failures. And if you don't have any diagnostics, then arguably these are all undetected failures. Then if we look at a ball valve, we can talk about no movement, which would be dangerous. If we have a leaky seal and cannot stop the flow, depending on the tightness of the shutoff requirements that we have, that will be a dangerous situation as well. Again, we need to take application issues into consideration. What's the actual environment? And what is the level of tight shutoff that is necessary. So if we do a detailed analysis on a product, on an equipment item, a transmitter, a valve, actuator, etc., we know what the dangers and detected failures are of that product. And keeping in mind that the objective of our proof test is to detect failures that are undetected by automatic diagnostics, we would be able to specify pretty detailed proof test procedures. This is something that is published by Rosemount for their 3051S SIS pressure transmitter, which is a safety certified SIL 2 single use, SIL 3 redundant use transmitter. And they have specified two different proof tests. One is a proof test where you can claim up to 65% coverage on the dangerous undetected failures, and one is a proof test where you can claim up to 98% coverage on dangerous undetected failures. So one of the key things here is that there are two different tests, and I'll go through them in just a bit, but the manufacturer of this product already identifies that, hey, Mr. or Mrs. End User, you are not able to detect all potentially undetected failures in this product. The manufacturer doesn't claim that their most extensive test will provide you with 100% proof test coverage. So if we go through the tests real quickly, the first test is called the analog output loop test, where you're required to enter the milliampere value representing a high alarm state, check the reference meter to verify the milliamp output corresponds to an entered value, enter the milliampere value representing a low alarm state, check the reference meter to verify the milliamp output corresponds to the entered value, and then finally execute the master reset command to initiate startup diagnostics. So if you perform this test, and in this particular case, the manufacturer says you can do this once every 5 years, you could claim up to 65% diagnostic coverage. And they've defined the 10-year test, which is the proof test, and when you combine this test with the analog output loop test, you will get 98%. So you would have to perform the first test, also known as the 5-year test, and then perform a minimum 2-point calibration check using 4 to 20 milliamp range point. Check the reference milliamp meter to verify that corresponds to the pressure input. If necessary, use a trim function and then execute master reset command to initiate startup diagnostics. So these are proof tests that a manufacturer has published that tell you the effectiveness of that specific test with regard to the detection of dangerous undetected failures. Now, if I run a quick calculation where I calculate the average probability of failure in the month for two scenarios, one is that pressure transmitter with 65% proof test coverage, one is that same pressure transmitter with 98% proof test coverage, you will see that the top line, which is the 65% coverage, has a 1.5 E-2 probability of failure on demand, and the bottom line has an average probability of failure on demand of 3.37 E-3. So there is almost an order of magnitude difference between the calculated average probability of failure on demand for the same transmitter, but with different effectiveness of the proof test coverage. Now, keep in mind, this is just one device of an entire safety instrument function, so we shouldn't be really concluding any SIL levels based on this calculation, but let's assume that the pressure transmitter is the limiting device, that the final elements and the logic solvers are both in the order of, let's say, 10⁻⁴ probability of failure on demand, then you could see that that the effectiveness of your test will change your SIL level by an order of magnitude. So this is, again, PFD as a function of time, and then also PFD average for the two scenarios. So that is basically what average probability of failure demand, how it reacts to more extensive proof test coverage. Now, how do I determine my proof test coverage? Well, and this is just as an example for a situation where I have an actuator valve combination,
I have a set of failure rates. One is provided that indicates the failures for a normal operation. There are certain failures that will result in safe undetected behavior. There are certain failures that will result in dangerous undetected behavior. And then I also have sets of failure rates for situations where I do partial stroking and one where I do full stroking. And if we assume that my full stroke test is the proof test that I perform, then we can very quickly calculate the proof test coverage without the partial valve stroke testing. So basically we compare the normal operation failure rate column to the full stroke test performed column, and we see that 841 failures or fits representing certain failures will be classified as detected, or this is stuff that I can detect when I perform a full stroke test, of the total 1,075 fits of that particular actuator valve combination. So from that I can calculate that I have a 78.2% proof test coverage. Similarly, if and I'll get to your comment later, Joe. Similarly, if we would do a partial valve stroke test, then the difference between the failures that are detected during the partial stroke and the failures that will be detected during the full stroke is much smaller, and you can quickly see 494 as undetected during the partial valve stroke minus 234 that undetected after the full stroke. That will give you 260 as number of failures that are detected divided by the total number of undetected failures, 494. You see in that case you only have 52.6% proof test coverage. So based on the application of your, in this case, actuator valve combination, you may end up with different proof test coverages given certain tests that you perform as a function of your proof testing. So PVD average with and without partial valve stroke testing, and again I run these two scenarios and you'll see that there isn't a whole lot of difference here. Arguably the proof test coverage on the actuator valve combination for the situation where I do the full stroke is not that great, and this is something to take away from this as well. I've seen some people claiming high levels of proof test coverages on valves if they just demonstrate that the valve closed, but there's definitely not sufficient coverage for all potential dangers of detected failure at that point. So what do we need to do from a proof test documentation perspective? We need to document all the results, test details, personnel, the date, bypass authorization, test performed, results, that the system was restored, so bypasses were removed. And the data from the proof test should be analyzed to find equipment problems. Before I go into our Excelencia software, I'll try to address the two comments that were made here. The first one was, must we make a leak test of a block valve? Is it possible to do this inline? It all depends in that when you perform your proof test on a block valve, the question is, what is the objective of the block valve? If it's just to stop flow and you can tolerate a certain amount of leakage, then arguably there's a certain amount of failures that you do not care about, arguably that you don't necessarily need to detect in order for your safety instrument function to be successful. However, if you perform just a full stroke on a block valve, then typical proof test coverage suggests that you can claim something in the order of 75%.
if we look at performing a proof test where you do a full stroke in combination with the leak test, then typical FMEDA results suggest that that you can get up to like 90% proof test coverage. So let's say full stroke just 75%, full stroke plus leak test 90%. If you run your calculations, that could be a drastic impact on the calculated average probability of failure in the month. You may have enough leverage in your SIL calculation where you say, well, I don't need to do this extra leak test. I'm fine enough, as it is with just a full stroke. So it all depends on the particular situation. Now, can you do it inline? Yes. Assuming that you have, let's say, a transmitter, pressure transmitter before and pressure transmitter after the valve, you can do by just looking at the differentials there. You can perform some leak testing. There are some manufacturers that are looking actually into X-ray type devices where there is a way to basically judge the tightness of the shot, tightness of the full stroke, to allow you to determine if it's safe enough or not. I don't know how far those developments are, but that is something that I heard when I visited one of the manufacturers. So I hope that answered that question. Then one other aspect, and this is where not necessarily want to say the different schools of thought show up, but the objective of the proof test is to detect undetected failures. And manufacturers know what those undetected failures are. They know their product. So if you look at the internals of a transmitter, there's nobody other than the manufacturer that can actually tell you what those failures are. So that's where proof test procedures, as I showed earlier, are very beneficial to the end user in that the manufacturer gives you an indication, hey, if you perform this, this, or this, you will be able to detect X number of failures. At the same time, and this is something that Joe brought up here, keep in mind the manufacturer is not familiar with the specific application. So your specific application may warrant some additional tests or additional detection measures that you need to implement to cover your application requirements. So that is something to keep in mind when we talk about this proof test and a proof test coverage. So for example, if you have a situation where a plugged impulse line is a big issue, then arguably the proof test coverage number that the manufacturer provides you only talks about the effectiveness of the test on the transmitter. It doesn't talk about the effectiveness of your test on impulse line or your ability to clean out those impulse lines. So keep that in mind as well. There's another question here. Bypass authorization. Please explain. Okay. In some situations, proof testing is done online. And again, this depends on plant philosophy, and not everybody wants to shut down to perform these proof tests. Again, every plant may have a different philosophy there. So there are some situations where you may want to perform a proof test of a device while your unit is running. And in that particular case, you need to temporarily bypass the safety function, because if you are, let's say, playing with a transmitter to perform various tests, then you may end up getting a wide range of process values, quote unquote, as an input into your logic solver. You may not necessarily want to trip on that.
So that's what the bypass authorization goes for. Now, another situation that I've seen in the past is where there was a master fuel valve where it basically determined that a proof test needed to be performed every year. However, operations did not want to shut down every year, and in this particular case, a bypass valve was installed that was normally closed, and that would be opened once a year when the proof test was done on the main fuel valve. And once the main fuel valve demonstrated it was doing what it was supposed to do, main fuel valve was opened up again, bypass valve was closed, and the system was restored to normal operation. So that's where the bypass authorization comes into play. There is another question here as to where can I find the PowerPoint. We do not distribute the PowerPoints, but we will make this webinar available as a recording later today, so you will actually be able to relive the webinar, and you can look at the PowerPoint at that point. So this is basically, in a nutshell, things to look at when it comes to proof testing. And yes, there are other aspects. People may want to make sure that when they perform the proof test that the application software in the logic solver is still the same, though theoretically the detection of or checking of the application software, make sure that the version is the same, will not detect any dangerous undetected failures in that particular logic solver. It's just a test if your modification procedures are acted upon, if people are doing what they're supposed to do. So if we look at the safety life cycle, there are in the simplified format several steps that we can identify. Hazard identification, where we try to answer the question what can go wrong. We do a PHA, HAZUP. Risk analysis, SIL selection, where we try to answer the question how bad can it be. We do layer protection analysis. What needs to be done is a question we try to answer when we do the safety requirements specification. How reliable is it? That's what we're addressing when we do SIL verification. And then finally, how do we keep it safe, or the sustainment of the certain specific SIL level. We have our Excelencia Safety Lifecycle Engineering tool with 3 base components: Select, SIF, SRS, and Silver. And we have several plugins. There is the PHA import plugin that will allow you to extract information from your PHAs and basically populate your list of potential safety instrumental functions. We also have a proof test generator plugin, and obviously that's the one that we will look at a little bit more detail in just a bit. Then we have a plugin that's called the SRS C&E plugin, which is basically the next step up for our SIF SRS tool, where we are dividing the SRS up into a process SRS, documenting the hazard information and the target safety integrity level, basically everything that we need to know in order to create a conceptual design and subsequent SIL verification. And the design SRS that documents all the assumptions that we make during the SIL verification. For example, proof testing. What is the proof test coverage that we assume? What are the proof test intervals? But also the voting arrangements, any partial stroke testing that we may have assumed, etc. So that is something that we have implemented in our SRS C&E plugin, which also creates cause and effect matrices. And that at this point is the Excelencia software. Now, if we focus on the proof test generator, and we need to keep in mind that the intent of the proof test is to detect failures not detected by automatic diagnostics. This is something that the manufacturer should know. The proof test report generator will allow you to create
a report with proof tests specific for the equipment that you selected during your silver process. And the test coverage factors for each component are indicated in the report as well. So as an example, in our Excellencia software, you can select proof test report, and this is just a single safety function as an example. But for example, you'll see here a certain device that limit switches that are used as a safety instrument of function input. Proof test interval was set at 60 months, and with a specific test listed, the manufacturer states you can claim up to 99% coverage on the failures that are typically undetected during normal operation. Again, keep in mind, you also need to account for the actual process. Manufacturer is not the one who's actually using the equipment. So you need to look at what applies to my specific application as well. Pass, fail, reasons for failure, etc., can be documented. And this is the proof test generator, which helps you in creating your final proof test procedures. In this particular case, final elements, we have a solenoid and an actuator valve. No, actually, this is just the actuator with specific tests for each device and a certain level of coverage that we can claim on those devices if you perform that specific tests. So this is, in a nutshell, what our proof test generator does. It will provide you with the tests that the manufacturer has identified as tests that you would need to do to detect failures that are not detected by automatic diagnostics during normal operation. Manufacturer, of course, knows the internals of the product, knows where the dangerous and detected failures are, and with that, it helps you in setting up your proof test procedures. Excellencia, we have a set of different platforms. We have an online version where, for those of you who are interested, where you can use the software while it's running on our server. We have single user or multi-user options there. We have a standalone product that will install the software on your local machine. You need a USB license key in order to run it. Again, single user, multi-user options available. We have a site license, which is pretty much the same as the standalone, except that the license key that comes along with it will allow 5 or 10 concurrent users. They all need to be on the same subnet. And then the other option is an Excellencia server, where you would basically install the application on the server, and your users would basically log into that server, pretty much the same as the users log into our online product. We offer training classes. We have a 1-day introduction to Excellencia, a 2-day advanced features, which goes into a lot of the parameters that we have available and explain how they can be used. And then we also combine our functional safety engineering lifecycle training classes with the Excellencia training class, at which point we end up with a 5-day total training class. So with that, we've reached the end of this webinar. Any questions? Feel free to ask. I see a couple here in the a couple of questions here. One question here is how can I find proof test coverage factor if I don't use automatic diagnostic alarming? Well, if you don't use the diagnostics in your device, then arguably all failures are undetected. And the typical proof tests that one is required to do by the manufacturer, or not required, that the manufacturer suggests, include an execution of the standard diagnostics. So arguably your proof test coverage is not going to be a whole lot different. It's probably going to be in the same ballpark order, if not the same. The main difference is going to be in the fact that during normal operation, all your failures are undetected. So you will not have any detected failures, which will drastically impact your average probability of failure on demand. A good question here. How do we know what proof test coverage to use for generic instruments? We have, with the proof test generator in Excellencia, we have also defined proof tests for generic equipment and proof test coverages for those tests. They are conservative estimates, but there are some coverages for the generic equipment as well. In an upcoming release of the Excellencia software, we will actually make the proof test coverage estimator available to all users. So you will be able to click on a hyperlink in Excellencia, and basically from that get the proof test coverage for the different equipment items that are part of your safety instrument function, as provided by manufacturers or as estimated for generic instruments. I have someone who can't hear me. I assume everybody else can hear me. Try and check your speakers, if I may ask, your PC speakers. Any other questions on this proof test design and planning webinar? Keep in mind the webinar is recorded. It will be made available later today. So if you want to have a listen at things we talked about today, feel free to check back in later. You can go through the webinar or provide the webinar link to someone else who wasn't able to attend. If there are no other questions, then I will stop the recording, and I will stay online for just a little bit longer, just so that if there are any additional questions, I will be able to answer those. Otherwise, thank you for listening in.